Alright, today we're doing the introduction to Redox, which you may or may not remember anything from Redox from Chem 1, but here we go. So it's recognizing a reaction as oxidation reduction, so you have to have a change in an oxidation number for at least two of the items, and then assigning oxidation numbers to elements and compounds. That's what we're going to focus on today. A redox reaction, there's two ways to describe it. Essentially, the old term is oxidation by oxygen. However, redox reactions don't have to include oxygen. So the old definition occurs in any chemical reaction in which oxygen is added to a substance. So this really almost is entirely defined by chemical reactions. Sorry, I missed a couple of subscripts here. You can fix those if you want to. The newer version is oxidation by electron shift, because that's how a reaction happens. Electrons are transferred, moved, gained, lost, something along those lines. Oxidation occurs when you lose electrons from an element. So we have this little device over here, little mnemonic oil rig. It's oxidation is loss. And then reduction, gain of electrons by an element. So reduction is gain. Oxidation is loss, reduction is gain. Both of these are referring to electrons. So for example, in this calcium plus some sort of acid apparently makes calcium ions and hydrogen gas. Calcium solid is elemental. It has a 0 oxidation number. The hydrogen is a +1. So the calcium has gone from 0 to +2. Its charge has increased, which means it's lost electrons, and therefore it's oxidized. And then for the hydrogen, it's gone from +1 to its elemental form, so that would be 0. So its charge has decreased, or it's gained electrons, and it's reduced. To determine the oxidation numbers, there is a whole bunch of rules, but the good news is really it's just the same charges that they form from the periodic table, most likely. Plus a couple of additions. The first one is that a free element, or anything in its normal state, has an atom of 0. So whatever it is on the periodic table, if it's listed as a solid on the periodic table and it's a solid in the equation, then it's 0. If it's listed as a gas on the periodic table and it's a gas in the equation, then it's 0. For a monatomic ion, the oxidation number is the same thing as the charge. So that just means, like when you're looking at group 1A, that it's a +1. Okay, group 7A is a -1, etc. Fluorine is only going to be a -1, no matter what. Chloride and bromide can actually do some other things and do some sharing and such, but fluorine can really only do one thing. Looking at the next one, chlorine, bromine, and iodine are always in -1 unless they're combined with oxygen or fluorine, which really doesn't happen that often. And then number 5, oxidation of hydrogen is +1 with a nonmetal, and -1 when it's bonded to a metal. So something with a nonmetal that would be like HA, so probably like an acid, and then if it's bonded to a metal, MH, so some kind of a hydride. Number 6, oxygen, is a little fishy. Almost all the time, it's going to be a -2. You have to watch out, however, for the peroxides, because once in a while you will have those show up. You have to look at the metal that it's bound to, or even non-metal that it's bound to figure out the charge. And then finally, this is our gift. The algebraic sum of everything in the whole compound has to be equal to 0. So if it's all of the ions have to equal up to 0. If it's a polyatomic, like PO4 -3, overall its entire charge has to equal -3 when you add them up. Alright, in exercise 9, we're going to determine the oxidation numbers for the elements. We're going to follow the rules that we just went over. We have a compound here for H2S. Alright, we have hydrogen that is paired with a nonmetal, so that indicates that that's going to be a +1 charge. Typically the overall, I guess, standard for the way of writing this is to write the oxidation number at the top. And then if you need to do any math or algebra, kind of bookkeeping stuff at the bottom. So you have 2 H pluses, so that gives you an overall charge of +2. Sulfur is in group 6, so it is most commonly a -2. So just to make sure, +2, and then that has to be a -2 to get us an overall charge of 0. So the oxidation numbers for H is +1 and sulfur is -2. Okay, sulfur itself, S8, well, that's a solid. That's its elemental form, so that's just 0. SCl2. Now we have 2 nonmetals here that are paired up. When you have a situation like this where you kind of expect both of these to be negative, the more electronegative it is, meaning the more toward the halogen side, that's what you want to start with. So in this case, you're going to start with the chloride. It's going to be a -1, and there's 2 of them there. For this compound to work out, to have a 0 charge overall, sulfur then has to be a +2. Alright, the next one. Sodium sulfite. Alright, again, here you have three elements to contend with. When I work with these, I want to always say work from the outside in. You have 2 things that are really never going to change here. Sodium is always going to be a +1, and oxygen is always going to be a -2, unless it's a peroxide. So if we consider what we have 2 sodiums, so that's +2 overall. We're not sure about the sulfur. And then we have 3 oxygens. 3 times -2 is -6. So we just have to figure out what goes in here. 2 plus 4 minus 6 would give us 0. So then the sulfur is a +4. And then finally, sulfate ion. This is the first one that we've seen where you have a charge to contend with. For the sulfate ion, again, we have oxygen present, so that's a -2. There are 4 of them, so the overall that's going to be a -8. Because the ion has a charge, it's -2 here, and so we just have to figure out what sulfur is. So in this case, 6 minus 8 gives us -2, so the sulfur is a +6. Alright, your activity series. Once you have created your activity series, hopefully you have that with you and you can kind of look at that. You also have an activity series in the form of the standard reduction potential chart that you have on the back of your periodic table. So that is a very large activity series. Okay, so oxidation of metals by salts and acids. These are essentially considered to be single replacement reactions. You can see in this case that you have an element in A, switches place with the metallic portion of the compound Bx, and then you have the opposing element and compound as a result. And these things do require a change in oxidation numbers. So initially, we don't know, what B would be, but A, because it's an individual element, would have an oxidation number of 0, and then B would have something that would be positive, and then on the other side, A would be positive and B would be 0. So if we take a look at exercise 10 and we write the balanced equation and determine which element is oxidized and which is reduced. The first one says solid copper reacts with aqueous silver nitrate. So we have copper solid, and then we have silver nitrate, AgNO3, that's aqueous. We have two metallic things that we're looking at here, so those are going to probably change places, which will leave us with copper, and the more common form is the copper 2 nitrate, and that would then leave us with solid silver. And the copper nitrate would be aqueous. Okay, let's see if we have a balanced equation, which it does not look like we do. We need 2 silver nitrates and 2 solid silver. Now we have to figure out which is oxidized and which is reduced. So we have to label the oxidation numbers to do that. Copper is an elemental, so there it is, 0. Silver is always a +1. If you have a polyatomic ion like this and it's grouped and it stays the same, you can just do the whole thing. That's a -1. Over here on the other side, our copper 2 nitrate. Well, our charge tells us what it is, copper 2, and nitrate stays -1. And then now we have elemental silver, so that's a 0. So then I can come through and I can sort of list the changes. Copper is going from 0 to +2. It's increasing in charge, or it's lost negative charges, it's lost electrons, so lose electrons, oxidized. The silver, on the other hand, has gone from +1 to 0, so it must have gained electrons, therefore it is reduced. We're also going to talk about the idea of oxidizing and reducing agents, and essentially they are the opposite of what happens to it. Something that gets oxidized caused the other something to be reduced, or the other. To finish the previous experiment, the reducing agent and oxidizing agent are as noted up here. The material that gets oxidized causes the other one to be reduced, so we call it the reducing agent, and the material that gets reduced causes the other one to be oxidized. Or sorry, I said it the other way. Yes, causes the other one to be oxidized, so it's the oxidizing agent. The next example is B. Aluminum reacts with hydrobromic acid. So we have solid aluminum reacts with hydrobromic acid, aqueous. Again, a single replacement reaction. In this case, the hydrogen is acting as the positive ion. So we have now aluminum bromide. We have to make sure that those charges balance. Aluminum is a +3, bromide is a -1. And then we have H, can't have that by itself, so it's hydrogen gas. That's also aqueous, and that's a gas. So at this point we need to identify the oxidation numbers that we have. So let's do that in the other color here. Aluminum is a solid, that's its standard state, so that's a 0. Hydrogen is linked with a nonmetal, so that's a +1. Bromide is linked with a metal, bromide is always a -1. On the other side, aluminum paired with bromide, bromide is a -1, aluminum is a +3, and then the elemental hydrogen is a 0. Now we can go through and compare the changes in oxidation numbers. Aluminum goes from a 0 to a +3, and then hydrogen goes from a +1 to a 0. So in this case, the aluminum has increased in charge or lost electrons, so it's oxidized and is the reducing agent. And then the hydrogen has gained an electron, so it is reduced and is the oxidizing agent.